Hello, we are going to look at this unit, which I've called Unit 16 because I had to give it a number, and it's all about simple machines. So part one here, we're going to go through kind of how simple machines work and what they do, and then in part two, we're going to work a bunch of examples. So what is a simple machine? A simple machine is a machine that makes work easier, but it doesn't decrease the work you have to do. And often, not always, as it seems to apply here, so we'll add a little caveat. Hold on, let me find my pen. Yes, give me my pen. Okay, so often, not always, but often to make the work easier on you, you have to apply a smaller force, but you apply that smaller force over a large distance. Okay? So the machine is a closed system and cannot increase the total amount of energy because energy has to be conserved. We have to be able to keep track of it one way or the other. That doesn't mean that we're not losing energy, and that's going to come into play when we talk about things like mechanical advantage and efficiency. We have to be able to keep track of all of it, even if some of it is lost. Okay, so there are many types of simple machines, and depending on which list you look at, you'll get a slightly different version. This one seemed to cover most of them. So we have inclined planes and wedges, which are really variations on the same thing. We have levers, like a hammer. Wheel and axle is a good one. We put in energy to cause the wheel to rotate, and that causes the whole thing to move forward. A screw, we turn the top and the whole thing moves in. And then pulleys. Okay. Regardless of the type of simple machine, simple machines have what is known as mechanical advantage. The mechanical advantage is a number, it's unitless, that tells you how many times a simple machine multiplies the effort force. Okay. In an ideal case, we're not losing any of the effort we're putting in due to friction and things like that, and that gives us the ideal mechanical advantage. But in the real world, we do have we do have friction and things like that, so we have to look at the actual mechanical advantage as well. Okay. Regardless of what sort of system we're looking at, the mechanical advantage, whether it's ideal or actual, is what I'm trying to say here. Mechanical advantage is always equal to how much force am I getting out divided by how much force I'm putting in. So remember, mechanical advantage, I said it multiplied by the force. If we rearrange this formula really quick, we get F in times the mechanical advantage is the force out. So ideally, you would like that mechanical advantage to be as big as possible so that you get as large an effect as possible, potentially. Sometimes you want it the other way around because you want to be able to put in a little force and get something bigger out. Just depends on what, forgive me, I said that wrong. Sometimes you want it the other way around. Sometimes you want the force you put in to be small. You get a small force out. And that's okay because you're getting a trade-off with distance. Okay? If we think about our system, really what we're thinking about is conservation of energy. So the work you put in equals the work out plus whatever is lost for other things like friction. Now we're looking at the ideal case, so this goes away. So that gives us that the force you put in, I forgot the subscript, is the distance that results from what you're doing. And remember, there's this cosine theta term that comes in for work. And that is the force out times the distance it moves out, and there's a cosine term there as well. Okay. Now, these two angles don't have to be the same, but for a lot of what we're doing, we're going to assume that they are. In that case, then the force in divided by the force out will equal the distance out times the cosine of that angle, which I'm, again, not subscripting them because often they are the same, divided by the input distance times the cosine of the angle. So this allows us, oh, and I rearranged it backwards, but hopefully you can follow what I'm doing here. Mechanical advantage is force out divided by force in. Notice that this one here and that one there are the same thing, just flipped over. So I'm going to flip this one over to plug it in. Okay. And again, assuming the angles are the same, which is often the case, then the distance that the input moved divided by the distance the output moved is equivalent to the mechanical advantage, force out divided by force in. So we have two versions of this formula for the ideal mechanical advantage. Okay. For actual mechanical advantage, the actual mechanical advantage is just the output force divided by the input force. But in this case, we have friction we have to deal with. Friction does not equal 0, which means I'm going to put in effort. I'm going to apply a force, and not all of that force is going to go into whatever happens on the output. Something's going to be lost. So this ratio is not going to be 1 most of the time when we think about the actual mechanical advantage. Okay. The last piece to think about is efficiency. So efficiency, by definition, is the output work divided by the input work. Okay, and again, we can plug in that work is force out divided by distance out. Oh, I had an equal sign where I shouldn't, which is force in divided by distance in for the input work. And if you think about this ratio, this is the actual mechanical advantage, this guy, divided by the ideal mechanical advantage, which is this piece. But notice again, it's upside down, so you have to put it in the denominator. Okay, and yes, there should potentially be cosines there, but I think most of the time, again, we can ignore those. You can also think about efficiency in terms of power. So power, remember, is work divided by time. Well, the time that is needed to put the energy in or do the input work and the time that the output's going to happen are going to be the same. So the time piece of it cancels. And so you can rewrite the work out as the power out divided by the power in. Okay, that completes this section.